collapse to a single condition, but the speed on the free surface is a constant, which is q. And I think this is really kind of why we can do a lot of the analysis now, is that, and it seems surprising that usually you have to have these two conditions, the kinematic and the dynamic boundary condition, and in this particular case, they collapse nicely to a single condition. It's still non-linear, but it's only one condition. So so the idea is to solve this equation, and it seems it seems ridiculously elementary. This is where it's dangerous, because I'll probably put a typo in some of these things. So here we have the Poisson's equation in the physical plane. So I've emphasized the x and the y independent variables, and we're going to change the independent variables to z and z bar, and you get this thing here. So these are complex variables. We get this 4 because of these transformation rules. We get this division by 2 there. And we can integrate this. We can integrate this once with respect to z bar to get, well, that's a constant, so omega 0 z bar plus an arbitrary function of z, which is c there. Using the fact that the stream function satisfies these, and the velocity as related to the stream function in this way, it means this is true. And then combine it, so we know that the velocity can be written in terms of the stream function like this, and so therefore combining 3 and 4, we get an expression for the fluid velocity in the entire domain in terms of this arbitrary function, c. So it's just a few lines, we get the fluid velocity. This is the solution to the whole problem. But we do need to find c. So how do we find the arbitrary constant? Well, we have to use the boundary conditions. So on the free surface, we only have the boundary condition is that the speed is constant. So that means that the velocity is equal to q, which is what the speed is, times by the tangent vector. In complex variables language, that statement is simply this. We want u minus iv, so we can write it like this, which is dz ds, which is the arc length. We can conjugate it. And then using the fact that ds and the arc length can be written like this, we end up with, on the free surface, u minus iv is equal to q times the square root derivative of z, of s, where s is this Schwartz function, which Darren introduced on Tuesday. And this s is equal to z bar on the free surface. So this is the velocity field on the free surface. We can combine it with our expression for it in the bulk, and eventually we get down to an expression for the fluid velocity which satisfies the boundary conditions and is true inside the bulk equation. And the only thing which is left to do is to find this Schwartz function. So I haven't specified how we're going to find this Schwartz function, but if we can find this Schwartz function, everything is determined through this really simple, nice formula. So so just to summarize that, this is what Darren's did, and it's in this very recent paper late last year. Started with this system here. With this solution here. That's the kind of summary from that. And I'm going to concentrate. And so he illustrated 3 different cases: case 1, a case 2, and case 3, depending on these 2 parameters. So there's a 2-parameter. The problem depends on 2 parameters, omega 0 and q. And I'm going to concentrate on the case 1, which is looking at that term there, which is so q 0. I'm going to concentrate on when we can write the solution like this. And Darren mentioned this on Tuesday. There'd actually been some work done on this case before in 2010 in this paper by Crowdy and Nelson, and they found a single parameter family of a single vortex row. Using a different formulation to this, actually, it was derived in an equivalent way, but a different starting point, if you like. And so this is for a single vortex row. And Well, I'm not a vortex. I didn't, you know, not an expert on vortex dynamics. But what I think of when I think of vortices, I think of this picture here. This was taken from Wikipedia. You have flow past experimental image of flow past the cylinder, and you get this kind of really distinct vortex street pattern. And here, instead of a single row, we have two rows. Upper row and a lower row. And it turns out, I mean, this is kind of completely classical. You can see it in LAN, that if you, in a uniform flow, in an uniform unbounded flow, you can have a steadily translating von Karman vortex street. And the velocity field is written exactly like that. As it turns out, it's not obvious this perhaps, or at least it wasn't obvious to me, if you add a shear flow into it, they don't exist. Maybe I'll be able to show you show you how that works later. And so we're coming up to the question. So the question which Darren asked at this summer school, or at least it was the question I thought he asked. Certainly, it was the question which I answered. Okay, so they don't exist in a linear shear flow if it's unbounded, but if you add a free surface on, do these vortex streets exist? So this was what I managed to show in my COVID hole. So now I'm going to construct a solution. So this is kind of a bit more of my contribution to the problem. So this is our velocity field. And the aim of the game is to find the Schwartz function, and we're going to construct a suitable conformal map, which will tell us that it's periodic. We want three conditions basically for it to satisfy. First one is that it's periodic. That's kind of easy. Second one is that it's steadily translating. It turns out this is the kicker. Getting it to be steadily translating. This is where the kind of interest in maths comes from. And we want it to correspond to point vortices. So part one and part two are kind of straightforward. Part two is the kicker. We're going to set omega 0 to 1 without loss of generality. I think that sets a time scale or something. Darren isn't here to be able to bail me out on that, which is annoying. Anyway, let's get on with it. So here's our physical plane. And here's our unit disk, and we're going to attempt to construct a conformal map from our physical Z plane to our complex zeta plane. And the free surface is going to be mapped to the boundary of this disk, and here's a branch cut. We're going to put a couple of vortices in, and there's two configurations. So here, this is a configuration where the vortices are in line, so they're directly on top of each other. And these are going to correspond to positions in the disk. So how does our map go? Well, we want periodicity. So we're going to have this I log zeta term. So that ticks off periodicity. That's straightforward, I guess. And then for these two vortices, we're going to add these two terms here. We have this uppercase A and B. And we've got to decide what are our control parameters and which ones are our unknowns. It's going to turn out we're going to let little a and little b, which correspond somehow, as I'll show, to the position of the vortices in the zeta plane, not in the z plane, but in the zeta plane. Lowercase a and b, we're going to set them as control parameters. Capital A and capital B, which it relates to the circulation, the strength of these vortices is going to come as part of the solution. This D here is also unknown, and this sets an origin. So we have to set an origin somewhere. And so I think we set one of these vortices to be always at -1, level of -1, I think. Or no, maybe even minus pi. But it's trivial, and yeah, it determines. You have to find D, and I've already talked too much about it, so I'm going to shut up and move on. Okay, so we want this map to be analytic in the disk. So this means that A and B have to be outside. And for these inline configuration, they have to be the same sign as well. There is the other configuration, which is the staggered case, or as we say in Norfolk, vortices on the H. If anyone's expression, maybe not. Maybe a few people here. So these vortices which are on the H, you have to have A and B different signs, and this corresponds to one of the vortices being gone on the other side of the imaginary plane. And I'm going to emphasize here, A and B are set and known, and uppercase A and B are to be determined. Right, so this is our map, and so we need to find out what A and B are, and this comes from this steadily translating condition. So let's construct the Schwarz function. So we start with the map, we conjugate it. So here's just writing it in terms of zeta bar, and then we know on the disk zeta bar is equal to 1. And so we can replace zeta bar, wherever we see zeta bar, by 1 over zeta, and we end up with the Schwarz function, kind of almost elementary calculation. And this is nice. What you see here, and I've highlighted these terms here, is that whereas the map was analytic in the disk, the Schwarz function isn't. There's poles at 1 over A, 1 over B, and this corresponds to the point vortices. And so now we need to look at the velocity field near these point vortices. So you can do a local expansion near the vortices in the Z plane. It's really important you do it in the Z plane now, not the zeta plane. So this is a bit of work here. I haven't had to work too hard so far, but this was a bit of work. And you end up with this kind of constant function, this SA, which is a horrible mess of functions involving all of the lowercase a's and the lowercase b's. This term here corresponds to the kind of singular velocity near the vortex. And to say that they're steadily traveling, we have to insist that this term is identically 0. Gives us this condition here. So this is this horrible mess you have to work out. So this is one condition for the uppercase A and uppercase B. We need another one. And it's not too difficult to realize that we do have another vortex. So this is as we go to one of the vortices, we can do similar analysis next to the other, and we end up with a pair of algebraic equations, which can eventually be written as this. And lambda and the lambdas and the mu's are horrendous functions of the lowercase a's and lowercase b's. Now, and solving this for A and B then solves the problem, because this insists that because we don't know what uppercase A and B are. So if we can solve these for A and B, we get what they are, and we can construct a solution to the problem. And this should be easy, yeah. I mean, this is a power 2. There's 2 quadratic forms, and we should be able to do this. And in fact, actually, so there's this theorem, Bezout's theorem. I don't know if anyone has heard of it from algebraic geometry. It's a bit scary, that, and we're already going into ideas which are way above my pay grade anyway. So 1779, Bezout's theorem would says that basically you look at the highest power in each equation, which is 2. 2 times 2 is 4. There should be 4 solutions. This seems reasonable to me, yeah? I mean, it should be reasonable to everybody, yeah? And so what you do is, okay, well, I'm not going to do the algebra. I usually do numeric. So I was really excited here. I was like, brilliant. I can finally use some computer algebra and just get the answer, and I'm done with it. And you do that, and unbelievably, the coefficients are too complex for, I tried it with Maple, MATLAB, and it's too complex. It says, no, thanks, I'm not going to do it, which is crazy. I mean, this is like 2 quadratic forms, yeah? You can't do that, then what's the point, you know? Maybe one of these AI bots might be able to do it. I don't know. But anyway, it turns out, so you huff and you puff and you substitute double precision numbers in, and then you can get a pair of solutions. But it turns out it was really consistent. Only 3 pairs of solutions emerged. And so this is where I had to go down this rabbit hole, really, because I looked at this and thought, well, surely there's got to be 4. And I only ever got 3. So something's going on here. I've either made a mistake in the coding, completely possible, or something else is going on. And it turned out something else was going on. It's easy. I mean, these are 2 hyperbole. If you think of these in the A, capital B plane, these are 2 hyperbole. And it turns out a couple of miracles happen. The first one, not really a miracle, it's just a nice coincidence, really. That you have to show this. You can't just rely on the computer algebra to tell you this. You have to show this. This is when I was thinking, what's going on here? This lambda 1 and mu2, they disappear. They're identically 0 for all values, and there's no reason of knowing that. You have to show it. The second one, which I think is genuinely kind of weird, is that this combination of coefficients identically vanishes, and that means that this can be, these 2 pairs of equations can be reduced to a cubic, which is the 3 roots. This is where you get the 3 things from. And there's no way of knowing that, I mean, you have to just kind of do brute force and then realize that this combination of coefficients knocks out the quartic term.
You don't mean lambda 2 to be in both.
Okay, yeah, possibly. There's, yeah. Let's check that in the preprint as well. Yeah. Right, yeah, so what about Bezout's theorem? For those of you who really care about it, apparently the missing root is a projective intersection, whatever that is. The 2 hyperbole intersect at infinity, but I'll leave that. I'll leave that as an exercise. Yeah, so yeah, I mean, so this is kind of, I mean, it's kind of trivial, but it's also it was kind of a bit of fun. I mean, you have a week and you're all alone, feeling a bit sorry for yourself. This was kind of fun going down this kind of rabbit hole. Anyway, so got to the bottom where there was 3 real roots, or sometimes 1 and 2 complex. Right, so now let's show you some of these solutions. So all of the, and this is just to illustrate how simple this is. All of these solutions are just constructed from 3 simple formulas. The map, which tells us where the free surface is, the Schwarz function, and the velocity field, which you can get the streamlines from. 3 very simple formulas. So first of all, let's show you some kind of bifurcation curves. So this is for inline streets. I'm going to fix the value of lowercase a and vary lowercase b, which we have in the horizontal axis here, and uppercase a and uppercase b here. So here are 3 roots. Now, it turns out, really annoyingly, that actually there's for the inline streets, only one of them results in a univalent map. So, and this is something which is maybe a little bit unsatisfactory about this. You compute the solutions, and then you get something out, and then you're not guaranteed to have a free surface, which is kind of doesn't self-intersect and all of that stuff. And so here, this solid line indicates a region in the parameter space where we can get a valid solution. You get these 2 limiting profiles at 1 and at 3. We can look at the circulation at these points, and we find that at 3, one of the vortexes has basically disappeared because the circulation is going to 0, and at the other one, it's vice versa. So at these limit points, basically one of them has completely disappeared, similar to what Darren showed on Tuesday. So here's what these profiles look like with the streamlines and some colors to make them appear even more interesting. We have so the first one here, if we look at this one here, we get, this is the kind of similar shape to the Crapper wave, the Herr-Wheeler solution. Then it goes to this kind of vanilla kind of solution. And then you get another limiting profile where these, I mean, it could be that we could go even further and end up similar to the kind of things which John Mark, you showed with these circles. You get a larger region of bubbles, air region. And they stop basically when they touch. And it's really annoying. There isn't, I think I was chatting to Vera about this at some point. There isn't really any kind of neat way to decide when these solutions stop. You just have to kind of compute them and look by eye. You can get a condition, when they stop, but the condition is a quartic equation, which is more complicated to solve than the original thing you're doing anyway. So what's the point? And I do, yeah, by that time, I was feeling a little bit better and things were beginning to taste again. If we look at variant B, we can see this region validity increases actually. So for as the modulus of a magnitude of A increases, so these branches are for different values of A. As we vary B, we can see that the branches persist for longer, and we get some more solutions there. The staggered streets, however, it's a lot more interesting because sometimes you can get one real route and sometimes you can get two real routes. And that means there's going to be some limit points somewhere. There's a limit points, that means that we're going to get some non-uniqueness as well. So we can see here, this is a zoom into the solution plane. If we play the same game of fixing A and varying B, we get these kind of limit point here, goes round and we get some kind of non-uniqueness, which you didn't get in the single vortex case. And these ones look a little bit more funky. There's some solutions where there's some cusps now. But here's so this one here, this one, which corresponds to the kind of limiting profile here. Here we get it gets limited because a cusp forms. And we also get the similar kind of limiting profiles here where you get this bubble forming. As you vary both of the parameters, the solution structure changes dramatically. And there's a whole bunch of these limit points collide. And you can get with multiple kind of bifurcations, and you can get, you know, if you go from A as -2 to A as -14, the solution space is dramatically different. Here's some of the profiles here. This one's quite interesting in that it's a limiting profile, but you don't get the cusp at the edge of the periodic window. Kind of quite interesting cusphoidal shapes. So it turns out actually that we can map all of that. We know when this is going to happen because we can calculate a discriminant of these equations, and so we can map out so here we have the little a and little b, and here we have the regions where we have one real route and three real routes, and so all of the information about the bifurcation diagram can be written here, and this is kind of again completely exact. These points here correspond to where these limit points collide, these transcritical bifurcations. And so really that's the end of the story and how we can kind of construct these solutions. But there are a couple of kind of outstanding issues. First of all, how do these connect to the von Karman streets? How do they bifurcate from the kind of classical solutions? And so we can do that as that should be magnitude of A and B go to infinity, not AB. So have modulus bars there. What happens is they go to infinity and the influence of the free surface disappears. And how do they relate to the classical von Karman streets? So here's my video. I don't have any time dependence in the problem. So what I'm going to do here is I'm going to increase A and B, and the values are going to be recorded at the top, and you're going to see how the solution changes and what happens to the vortices. So A and B are getting really big. And so this is for the inline streets. And you can see there's a few jumps here. That's just because I'm changing the rate at which they increase. And you can see what happens is that the vortices basically merge. We end up with a flat free surface, and they merge, and it's kind of completely degenerate case. So they're not related at all, basically. They're just killing each other off, and we just end up with a flat free surface, and we just end up with nothing. But the staggered case as well. So here I'm starting at one of those limiting profiles, and I'm going to increase A and B. So here they have different signs, and we'll see what happens. So you can see this is quite nice. You can see how the changes from a bimodal shape to one modal. And if you've been looking at the free surface, you may have forgot to look at the vortex pattern. And so what happens here is that this is a solution. First of all, the free surface isn't flat. It's still kind of it's still wavy. And what we've got here is a single row of pi periodic vortices. So it kind of bifurcates from 2 pi, the periodicity halves. So we get pi periodic. So finally, where do we go from here? So this is really just a nice exercise in kind of how you can construct these elementary solutions, and that's what kind of appealed to me when Darren gave all of this framework on last year. But I think after listening to some of these talks as well, I think there's a natural question which comes out from all this. Vortex streets, the classical vortex streets, these are unstable, except for a really special space ratio. And even then, there's a suspicion that it's weakly unstable. But in general, these are unstable. The Herr and Wheeler waves, which we've been talked about, and kind of which my solutions are related to, they were proved by Mark and Emilian to be unstable as well. You have the waves without vortex is unstable, and you have the vortex streets unstable. However, in this Nelson and Crowdy paper, I mean, they're hidden away right at the end, they do some contour dynamics to test the numerical stability of a single row. And they have some very cryptic figures, and I've tried to nail Darren down on it, and seeing as he isn't here, too late now. I guess I could send him an email. But you get these figures here, where this is a time trace of a solution measure, where they nudge a single row of vortices and see what happens. And they do suggest, they say it appears robust to small perturbations. It appears robust to small perturbations. So that suggests that they're stable, or at least there's numerical evidence to suggest that it doesn't blow up. So here's the question. I mean, wouldn't it be great if a vortex street plus a free surface was stable? Both of these things in isolation are unstable. I think it would be a really cool result if the combination somehow two things interacting show that these things were stable. I mean, this is just a question which is just thrown out there. Some of you may know the answer.
Did they put general perturbations on that, or was it just perturbation of their complex variable solution? Because
they just moved the vortices up and down. They didn't perturb their free surface. I don't think they just moved it up and down, and they did lateral and vertical.
I'll make a comment on that.
Yeah, sure. Yeah, I mean, but they do comment in the paper. They say this appears robust. You kind of like. So there we have it, and this is in archive at the moment. Thank you very much.